Welcome back. Finally, this is the last tutorial of the entire series of this C-HiDeNN tutorial. Now we want to go into the convolution hierarchical deep learning neural network. I want to say in short as C-HiDeNN. Let's get started. In hidden FEM, remember that we converted the FEM interpolation function as a neural network. There's two hidden layers. They are not fully connected, right? And their weights and biases were functions of nodal coordinates and nodal variables. But there's a question. This is only a linear interpolation, and can we go to nonlinear interpolation, just like activation functions in neural network? The answer is yes, if we add additional hidden layer that accounts for the nonlinear interpolation. We call that convolution layer. Actually, there's an additional layer. I'll explain this later. But this is going to be our elementary neural network, and it goes into each element. So that's the idea. So the third hidden layer, this is called convolution layer, is where the magic happens. All right. So let's go step by step. Here's the same element diagram. But let's first look at element 1. So element 1 has node 1 and node 2. They are colored red and green respectively. And we define nodal patch. It's a support domain for each node inside this element. And this nodal patch is defined as S number of nodes to the left and right, where S is the patch size. For example, when S is equal to 2, the nodal patches for element 1 becomes, for node 1, it's going to be this 3 nodes. Patch 1 is x1 to 3. Because this from this red node 1, you have 2 nodes on the right, and there's no node on the left side. Okay, that's why you have 3 nodes for patch 1, x1 to 3. For node 2, you're going to have 4 nodes because you have 1 node on the left and 2 nodes on the right. All right. So based on this nodal patch 1 and 2, we can formulate the convolution layer. Node 1 has a nodal patch consisting of node x1 to 3. The corresponding those node x1 to 3, there's a nodal displacement u1 to 3 acting on this part. And on the second node, you will have node 1 through 4 involved, right? So this is how the elementary neural network is structured for convolution hidden. So now we move to element 2. This element 2 has node 2 on the left and node 3 on the right. And for node 2, the patch node, we call patch 2, consists of 4 nodes, x1 through x4. And on the node 3, the patch nodes are x1 through x5 because this node 3 has 2 nodes on the left and 2 nodes on the right. Okay? For this element 2, the convolution layer is constructed like this. For node 2, you have u1 through u4 involved, and node 3, u1 through u5 involved. So the actual nonlinear interpolation takes place inside this convolution patch function, the brown box, which is explained here. I don't want to cover this in detail, but they are all written in my paper, which is shown below. But the key idea, this paper. But the key idea is the nonlinear activation is dealt with within this brown box called convolution patch functions. So the output of this convolution patch function, W1 through Wn, they are going to be acting as a weights between the second and third hidden layers. That's the idea. All right, based on this setup, we want to solve the same problem with C-HiDeNN, but with patch size s equals 2 and the polynomial order, the nonlinearity of our interpolation, as 2, which is we can reproduce up to second order polynomials. because C-HiDeNN can reproduce up to second-order polynomials, the error of C-HiDeNN approaches to almost a machine error, very accurate. And also the stress field of C-HiDeNN is linear, which is the same as the exact solution. Remember, this is the reason why I picked this simple quadratic polynomial function as an exact solution, because if we set up this, C-HiDeNN can exactly reproduce the exact solution. It's quite a simple trick, you know. So, all right, let's go back to the code and finish this tutorial. So, going back to our main program, right? So, I want to set this C-HiDeNN or CFVM as true. So, I want to set the patch size as equals 2, and the p is actually the polynomial order, but -1 of p means p is equal to s. So because our s is 2, that means our p is also 2. Alpha is a dilation parameter. That is a hyperparameter for building the convolution patch functions. The details can be also found in the same reference paper. There are 4 elements, and this is element type. All right, so let me run it. And you will see down here, now it is plotting. Yes, you can see, right? It's amazing. The error is almost 0. All right. Thank you for listening the entire tutorial series, and you can debug this code whatever you want, but please keep in mind that this is we are doing the patent procedure, so you can freely use this for academic purpose, but we don't recommend you for using this for commercial purpose. Okay, so that's it for the tutorial. Thank you for listening, and hope to see you in the future in person, probably in UC Berkeley or Northwestern. All right, thank you. Bye.